Section 1.5 deals with functions and logarithms. First, we're going to talk about one-to-one functions, then inverses, finding inverses, logarithmic functions, and properties of logarithms. So first, let's talk about one-to-one functions. Now, right off the bat, you might think that this relates to even and odd functions, and that's correct. The way we can figure out if a function is one-to-one is by doing the horizontal line test. So on the left-hand side here, I have a one-to-one function, which means that if I draw horizontal lines, I only cross my function one time. The same cannot be said for the right-hand side, which is not a one-to-one function. It fails the horizontal line test. So if I draw a series of horizontal lines, I am crossing my function twice. And the textbook definition of that is if a function f of x is a one-to-one on a domain D, if f of a does not equal f of b whenever a does not equal b. And that's just saying the same exact thing. There are no places where we have two equal y values. A one-to-one function is never going to have two y values that are the same, and a not one-to-one function is going to have two or possibly more y values that are the same, even with different x values. Now, an inverse function is when we take the domains and ranges of another function and we flip them. So we have a function here, f of x, where 1, if we input 1 for x, it's equal to a, 2 is equal to b, 3 is equal to c, and 4 is equal to d. If we invert that function, if we find its inverse, then we swap those. Our input values, a, b, c, and d, and output values are swapped. So whenever we have an inverse function, just know that the domain and range is going to be swapped for that function if it's an inverse. And here's a quick example of how we find an inverse function. So we have to show that the function y equals f of x equals 2x plus 4 is a one-to-one function, and we have to find its inverse as well. So we're actually covering both things that we just talked about. We're going to see if this function is one-to-one, and also we're going to find its inverse. So first, let's see if it's one-to-one. So we're going to first graph the function to see if it passes the horizontal line test. And you can use an online grapher or your graphing calculator, but I used my online graphing calculator. And I see that this function is just a line. And anytime a function is linear, aka it's a line, it's going to be a one-to-one function unless it's a constant, unless it's like a flat line like this. But if it's not a flat line, if it's a line that has a slope, a certain slope that isn't 0, then all lines are going to be one-to-one functions because there's no curves here. There's no place where we have two different where we have a y value for the function repeated. I guess if it's some parametric functions that are linear could have don't necessarily have to be one-to-one, but for the most part, linear functions, lines are going to be one-to-one unless they're flat. Okay, and so we can see that this passes the horizontal line test. Again, just draw a series of horizontal lines, and we're only hitting our function one time with each of these horizontal lines that we are drawing. So let's see what our next step is here. Next, well, it passes the horizontal line test as we just saw, and we can just do that graphically. Next, we're going to find the inverse. And how do we do that? Well, the first thing we have to do is solve for x in terms of y. So if we have y equals negative 2x plus 4, to find the inverse, the first step is we swap x and y. Sorry, we don't swap x and y yet. We just solve for x in terms of y. So we have y isolated in the first case, and now we're going to isolate x instead. So just some simple algebra, subtracting 4 from each side, and then we're going to divide each side by 2 to isolate x, and we have x is equal to negative y over 2 plus 2. So we isolated x, very simple algebra. And next we swap the x and y values. So wherever we have our y value here and x value here, we now swap them with each other. And that's going to mean that we have y equals negative x over 2 plus 2. So the inverse, our inverse function, to find that, we follow these steps. First, we isolate x, and then we swap x and y. And so if we were to graph this, here's what we get. We have our inverse function right here is in the blue. Our original function f of x is in the red. Our inverse function is in the blue. We just followed these basic steps to see if it's 1-to-1, and we found its inverse. And also, the inverse function is also 1-to-1 because it passes the horizontal line test. Each horizontal line we draw, it only crosses our blue line and red line one time, meaning that they are both 1-to-1. Next, let's quickly talk about logarithmic functions. The base A logarithm function, y equals log base a of x, is the inverse of the base a exponential function y equals a to the x, where a is greater than 0 and a does not equal 1. So this is a little bit confusing, but all a log function really is the following. So if we have a certain exponent, if we have a raised to the y and that equals x, if we want to write it in log terms, we just simply put this a into the base of the log, our x value goes over here, and our exponent, log base a of x, is equal to the exponent y. So it's just it's a quick way of rewriting exponential functions. It's a different way of rewriting exponential functions. So if we have a raised to the something is equal to x to something else, we can rewrite it like this. Log base a x is equal to the exponent. And a quick example of that over here, if we have a log of base 2, 8, log base 2, 8 is equal to 3, that means that 2 raised to the 3, right here, 2 raised to the 3 is equal to 8. So it's basically just rewriting exponents in a different way. And this becomes useful later on in calculus because sometimes we need to use this notation as opposed to a standard exponent. And logarithms have certain properties, so we don't need to go into too much detail about this now, but that'll come up later, where we have the product rule, where log base a of x times y is just equal to log base a x plus log base ay, so we can split the logs up into two different pieces. The quotient rule, similar to the product rule except dealing with division. We just have a minus sign right here. And again, this is a way of splitting up more complicated logs into something that we can deal with easier. And we have, of course, the power rule. So if we have a log base a of something raised to something else, an exponent within a log, then we pull that exponent out in front of the log and rewrite it as such. So the exponent, if we have a log, if we're taking a log of something that has an exponent, we can pull the exponent out in something known as the power rule. Product rule, quotient rule, and power rule is something you're going to hear a lot later on in calculus. These expressions are pretty common. But we also have this scenario here where we have a log base a of x. Log base a x is equal to ln of a, ln of x over ln of a. Now, ln, you're going to see this a lot as well. Ln is called the natural log. And if you could recall from earlier, we had something called the Euler number, e. Now, this is a place where this pops up. So ln is just log. It's just a log that has a base of e, which I recall was 2.8 something, I think. But e was a natural constant that pops up in nature a lot, known as the Euler number. So if you ever see log ln of x, that's the same as saying log base e of x. And that's going to wrap up section 1.5. dealing with functions and logarithms, just a brief recap of these subjects.